Let me give you some hints on how to organize things a little bit in assignment 3. Organizing files and folders. Because this can be quite important when you work with big data like we typically do here now in metagenomics, to organize yourself in folders. Because otherwise it can become very sort of difficult to keep the overview, I think. So let me just make some suggestions here now. So let's say that you have completed assignment 2 and you have an assignment 2 folder somewhere under your home, right, on Orion. Inside this folder you should now have at least these 4 FASTA files with contigs. Because in assignment 2 you made some assembly of Illumina reads and of nanopore reads. This one with metaspades, right? This one with metafly. And notice I'm only talking about the Illumina contigs that you got from the raw data, not the FastP, because you actually had 6 files in assignment 2. But forget about those FastP pre-processed data now. We only consider the raw Illumina data and the raw nanopore data. So that's why it's only 4 contigs here now that I show. These are in the assignment 2 folder. And these were made from the reads that are in this courses folder up here. And they are still there, right? Under this address here, under this path. You will find the reads that you used to create these contigs. And you will need this now for assignment 3. So assignment 2 results, some of them, are needed for the assignment 3. So what you typically now do, you create yourself a new folder, assignment 3, right, under your home somewhere. I don't care where, but I assume you have a assignment 3 folder. You should now, inside this folder, create 4 subfolders like this. I think this is a good idea. And notice there's one subfolder here now for each of these 4 sets of contigs, right? Inside here you have number of contigs, many of them. Inside here you have also many contigs, and here and here. The very first thing you're going to do in assignment 3 is to simply just read the contigs from this file, keep only those who have length 1000 bases or more, and store in this folder here. Then you do exactly the same here, and this is something you do in R, right? R code. Reading this FASTA file, computing the length of each sequence, keeping only sequences of length 1000 or more, and save it here. Write FASTA out to this folder, right? And then you do exactly the same for this one, put in here, the same for this one, put in here, and the same for this one, put in here. So now you should have one contigs file in each of these 4 folders. And they are not copies from here because they are smaller, right? You throw away all the short contigs now, those shorter than 1000 bases. So the FASTA files you get in here should be much smaller actually than this here. Yeah, perhaps not so much smaller in memory because you throw away only short contigs and they are not so big. The next thing you're going to do in assignment 3 is to compute coverage per contig. Coverage per contig. See module 8 for how to do this. And my point is then you work in each of these folders separate, or you make the script here. At least I would do that, but you do the job for each of these 4 in turn, right? You don't need 4 scripts to do this. You can do more or less the same in all 4 cases with some variations, right? Because here you need to use the bow tie, these are Illumina data, right? These contigs are based on Illumina data. And then you must go up here to see where are the reads from sample A, right? For your data set. Take those reads, map to the config in here using bow tie. This is module 8 stuff. And then you do the computation of mean coverage and variance of coverage and so on, like it says in the assignment 3 document, and store it in here as an abundance file or coverage file. I think we call it abundance file. Yeah, it's a 4-column text file only, with 1 row for each config, and then the config name, sort of ID, then the length of the config, the mean coverage of the config, and the variance of the coverage of the config. So there are 4 columns. Yeah, and then you do exactly the same here. You can use exactly the same script. You just change some names, right? Use the B sample reads against the B sample contigs here. But the rest is same. Then do the same for nanopore, but now you have to switch from using bow tie to minimap 2. That's the only difference really, because now you need to use the nanopore reads from up here, right? The nanopore A sample reads against the nanopore A contigs in here, mapping with minimap 2. And then exactly the same here. And in all 4 cases, you should get this table or this small text file with a sort of a table with 4 columns stored separately in each of these folders, right? So after you have done this part of assignment 3, there should be 2 files in here, a config file and a small text file with this coverage results, and the same here, the same here, the same here. Okay, that's it for now, but this video I will extend next week when we are launching module 9, because then there will be some further things to do here. But try to do this here now and organize yourself. I think this could be a good way to do it, have it in separate folders. And then you have the scripts on up here, but you read and save to the different folders depending on which dataset you are working with. It's important that we always do it like this when we are trying to do when we have contigs from different samples. We should sort of treat them separately for some time, especially this coverage information, right? It's very important that you take the A sample reads, map against the A sample contigs and not against the B sample contigs, for instance, because these contigs are made from a different sample. And if you take the reads from a different sample up here and map, the results mean nothing, right? It's completely waste of effort, really. Yeah, at least for this context, they mean nothing. They may mean something in another context, but here you have to make sure that you map the reads from the same sample as you have contigs from all the time. All the time. Okay, see you next week then. Okay, so in module 9 we talk about binning of the contigs that you have from the different samples. And this means you still work in these 4 folders, because from each of, for instance, this Illumina A bins folder, here you have the Illumina A contigs and you have the corresponding abundance file, and then you run the 3 binning tools, right? The maxbin, the metabat, and the concoct. All 3 of them on these bin on the contigs here, on the same contigs, right? But they will group the contigs slightly differently. So you will have sort of 3 sets of bins in this folder, and the same here, and the same here, and the same here. Notice that at this stage it doesn't matter if the bins or the contigs are from Illumina or from Nanopore originally. Contigs are contigs. So the binning tools are the same regardless of how the raw data look like, because now we are no longer on the raw data, now we are on the contigs, grouping the contigs. So the same procedure in all 4 cases, and output back to the different folders here, because you only bin the contigs from this sample and again from this sample, and you do this independently of each other, because when you bin the contigs here from this sample, you must use the coverages based on the data from this sample, right? And the same for all the other cases here. So after the sort of binning with the 3 tools, Metabot, MaxBin, and Concoct, you still have these 4 folders, but now you have lots of FASTA files in each of them, right? Then at the end of this sort of binning procedure, you are going to do what we call ensemble binning. And that means you take all the suggested bins from, for instance, this folder here, and you feed it to this DAS tool ensemble binner, and you output the results to a new folder here. And here I call this Illumina final bins. The point is now that from the bins here, you get some final bins here, but from these bins here, you also get some final bins here. And notice now, because here you now get a mix from both A and B sample. So it's really important that the bin files, the FASTA files with the bins, have something in the names that recognize this as A sample bins and this as B sample bins. Because when it come here, they are mixed together. So for instance, imagine you have a bin here called maxbin 001.fasta, something like that. Then you will also have here a file with exactly the same name. And if both of these survive this ensemble step, they will end up here, but since they have the same name, one of them will overwrite the other. So it's really important that the bin names you have, the names of the FASTA files with the bins contain an A here and a B here, for instance. That would be a natural separation, right? So that when they end up here, you can tell them apart, even if they have. And remember, these numbers that these binning tools add to the file names, they mean nothing, right? It's just a label. So it's not like bin number 1 up here has anything to do with bin number 1 down here. These numbers have no meaning at all. It's just labels. So you can easily have the same name, right? And also for the Nanopore, you do exactly the same ensemble binning here and put into a separate folder here. And why don't we mix all this into one super final bins folder? Well, it's because you're going to make a comparison in the end of Illumina versus Nanopore. So you must keep them apart. Otherwise, you will get a mixture of both, right? In some cases, that would actually be okay to do. But in this particular case, it's not okay to do, because then the whole purpose of this exercise is to compare what you get from the Illumina data to what you get from the Nanopore data. So you have to keep them apart. Okay, so then you have some final bins, sort of following this path and following this path. And then in module 10 you will make the mags, and then you will have yet another set of folders, I suggest, where you have the final mags following the Illumina path and the final mags following the nanopore path. So altogether 8 different subfolders. But that's I think that's a good way of splitting it. I'm not saying it's the only way. I'm just hinting here now how you can do it. You can do this in many ways, but at least this looks to me like a little bit sort of easier to overview if you need some sort of input for not messing up too much, because there are lots of files here now, right? 3 sets of bins here, different large number of FASTA files in each here, and of course it's not so large number of files here, but still enough, and here it's not at all very much, but that varies from dataset to dataset. Some of you will have few mags and some more, and then you will have to do the conclusion based on what you get here. Did the Illumina or the nanopore result in very different mags and different number of mags and so on? But that I leave to you to do now.